All right, on tonight's episode of Python Papi, we're back inside our artificial intelligence course, and we're still in our optimization module. Let's have a look at what we went over tonight. And yesterday we left off around this area here. We were taking a look at examples of our grids, our grid maps. And tonight, basically, we just made a bunch of different grids and showing the different states that we can move our hospital to get the cost lower. You can see we started at a 17. Let me get to the top. We started at a cost of 17. That'll be 17 spaces we would have to move all together to get our hospitals closer to each house. And we just moved our hospitals to their neighbors to get our costs down as much as we can. And we got all the way down to 11, moving the proper way. But then there was a move we can make to get down to a cost of 9. But let me read what's going on with this one. So we were able to move this hospital here from this location to this location moving diagonal. It wasn't actually a proper move we can make because we didn't define it. And it says, in particular, there are a number of ways we can do this, but one way is by taking the hospital on the left and moving it diagonally to a closer square, giving us a new cost of 9, which was not part of our definition of neighbor, where we could only move left, right, up, or down. So part of our definition of neighbors was that we can only move the hospital either left, right, up, or down. So moving diagonally from this location to this location wasn't really a possible move. So we weren't able to find it because in order to get there, we had to go through a state that actually wasn't any better than the current state that we had previously. Now, this appears to be a limitation or concern that we might have as we go about trying to implement a hill climbing algorithm, is that it might not always give us the optimal solution. So this was the best possible solution that we could have had for our hospital with the least amount of steps or the least amount of cost, but it wasn't actually defined in our move, so we weren't able to make or we weren't able to see it to actually implement it. So yeah. If we are trying to maximize the value of any particular state, we're trying to find a global maximum. A concern we might be that we could get stuck at one of the local maxima. Now, local maxima is any state whose value is higher than any of its neighbors. And the same issue can also occur when looking for a global minimum. You might get stuck in a local minimum. A local minimum is any state whose value is lower than any of its neighbors. So yeah, like I was saying, with this state here, 9 was actually our least cost effective model that we could use. But again, since it wasn't defined inside of our definition of neighbor, we weren't able to actually see it, or our algorithm wasn't able to see it to make it. So if we stuck to our rules, 11 would have been the most or the least cost effective move for us. And you can see the hospital here. So we moved it from here, we moved it to here using the diagonal, which wasn't defined. But yep, that's what we went over tonight. We did a bunch of graph making or grid making, and we just took a lot of notes. Yeah, things are still moving steadily forward. And if you're sticking with me, stick with me. We're going to keep moving forward. This is the Python Poppy. You guys stay Gucci.